So we've been kind of wandering our way here through the beginning of organic chemistry, which as we found out is kind of the boiled down and digested Gen Chem. And we've been spending quite a bit of time talking about the periodic table. And as I make this point in pretty much every chemistry class that I teach, starting from Gen Chem all the way up, the periodic table is where, a lot of foundational information comes from, right? And so just being able to read that and get comfortable with it and understanding it, and then being able to recall that information as you are working through the individual courses, that's going to be a big help for you guys, right? And so I think last time we had kind of ended up with this idea of what our electron counts, and that's kind of where we had ended with that. And so we had kind of tossed out a couple different terms here and there about what are, I think, what was the question itself? Where do electrons live, I think is what the question was, right? So we were kind of going around and figuring out where do electrons live, and we had kind of, were making our way discussing different points that you guys had thought about there. And I think that's where we ended up. So today we're just going to kind of continue talking about the periodic table and the periodic trends and some of these important things that I need you guys to just kind of have sitting in the back of your minds all the time, right? And I say that somewhat jokingly, right? But remember, the reason why I'm spending all this time reviewing something that you guys were already taught is because this is the foundation that we build all of organic chemistry off of. So if I just launch into organic chemistry and you guys don't have a solid understanding of what hydrogen bonding is or why it occurs, right? Then when I go and explain to you guys about reaction kinetics for certain reactions, you're like, oh look, it's going to be slowed down because of sterics due to hydrogen bonding. And you guys are like, oh yeah, sterics, hydrogen bonding. And then there's no understanding, it's just memorizing that comes with that, right? So I got to lay this foundation for everybody here, and then we can go through and we can kind of explain and understand what's going on with this. Yeah?
What's a steric?
We'll get there, don't worry. Yeah.
Okay. So
Okay.
I don't need to already know what that is.
Well, you already do know what it is, but well, don't worry, we'll go through it. Okay. Alrighty, so that's where we ended up. Let's see. I think we've got one lab section left today, right? Isn't there the Friday lab section? I think those are the slackers who signed up last. Is that what, I'm just kidding. No, I'm joking, of course. So we got one more lab section today, and that'll be the end of the first lab week. And then next week, we'll go through and we'll finish up the caffeine stuff there. Where's Dr. Barbosa's section from yesterday evening? How far did you guys get? You got through the extraction process at least?
Yes.
You got through that? Okay, that's fine. That's where everyone got to.
I broke a funnel.
You broke a funnel?
Uh-huh.
The $150 funnel?
Uh-huh.
Nice. All right. Well, so I got bad news. Tuition next year is going to go up, right? You guys are going to have to, account for certain losses of university instruments here. Okay. So
It still works. It just has some broken edges.
yeah. Oh, so it like adds an element of danger. Just what we want. All right.
Exactly.
It's all good. Alrighty, so now it looks like we're kind of on track with that then, and hopefully Dr. Barbosa kind of is going to talk to you guys a little bit about this too. But we're going to be talking about some things in class that are going to lead into some of the analysis that we expect you guys to do while you guys are in the lab there also, like the IR and the NMR, stuff like that, okay? So we got to introduce some topics here, and then we will talk about that a little bit more while we get into the lab, okay? All right, cool. So that all being said, let's get started with some prayer, and then we can continue looking at this stuff here. But Lord, we just thank you for another day, and we thank you for another opportunity that we can just gather before you. And Lord, we just thank you for the option, just that whenever we want, we can just turn to prayer with you, Lord, and that we can have a conversation with you for the things that are on our hearts, the things that are on our minds, the things that are distracting us, the things that are pulling us in a million different directions. Lord, you tell us that you want to hear from us and that we should talk with you and that we should lay these things before you. So Lord, for the things that are just distracting us from the calling that you've put in our lives, Lord, we pray that we just have the courage and the strength just to lay those before you, and that we just can understand that you want to help us carry these things, Lord. So we just pray for that understanding in our hearts and our minds, and we pray that we can just grow in love for you and for those around us, Lord. And we just ask all this in your name. Amen. Amen. All right. So, where do electrons live? What have we talked about so far?
Orbitals.
We live in orbitals. What have we said about orbitals?
You can only have 2 electrons.
They can only ever have 2 electrons in any kind of orbital. Okay? Now we are talking about a atomic orbitals at the moment, but eventually we will talk about molecular orbitals, right? So these are orbitals that exist in molecules as opposed to discrete atoms. Is there going to be any difference there? No, they can only still be up, I should be careful, I should say up to 2 electrons, no more than 2. We'll talk about the rare cases of free radicals, but so just as a caveat there in your notes, I guess up no more than 2 electrons can live in it. Predominantly 2 is what we're going to see, okay? So they live in orbitals. We talked about the different blocks of the periodic table, right? The S, P, D, and F blocks, and we talked about that. We talked about our principal quantum numbers and how that's our street address to figure out where the electrons are, right? We talked about, or at least reviewed a little bit about how to get the electron configurations for a specific element. Yeah.
Sorry, for the quantum numbers.
Yeah.
So you said that there are 4 things that we need to define where an electron is located.
Correct.
So then you talked about quantum numbers.
Yeah.
Are we supposed to know what each of them stand for? Like
Yeah, we'll get through it. Right now, I think we've only talked about N, right? The principal quantum number there, right? Which defines the energy level that we're dealing with, right? 1 through infinity is what it is, right? So that's remember what I said, when those blue numbers that are on the left-hand side there, those are just kind of to help us figure out what the energy level that we're dealing with is, right? But N is a principal quantum number, and we would say that it defines the energy level of the shell that we're looking at, okay? And it's technically infinite. Although practically speaking, you see, you can only really get up to 7, right? For what we know at the moment, I should say. Okay, so that's what N is, and that's kind of a good recap there. We didn't talk about the shapes of the orbitals yet, did we?
We talked about the shape of the S orbital.
Okay, we talked about the shape of just the S orbital, right? Okay, good. So the shape of the S orbital, right, is a sphere. We talked about where those shapes come from, right? It's not arbitrary. These are mathematical solutions to probability functions, right? That sounds kind of fancy. What does that mean? Smart people did math. They defined these shapes, right? There's an equation that can fall out of this that you guys could plug into some kind of graphing software and it will come up with the correct shape of these spheres, okay? And that's where the shapes of the orbitals come from. Is shape important?
Yes.
Yeah, right? And that's not my words, okay? If you go take a look at many of the great scientists throughout history, okay? Well, I believe it was Watson and I think it was Watson or Crick, I can't remember exactly which one it is, but one of their quotes is if you want to understand function, if you want to understand function, look at shape, right? So shape and function are inherently linked in not only biological systems, but chemical systems as well, right? So, and I think you guys at least have some kind of understanding about this. If you guys have looked at any kind of pharmaceuticals or, how do drugs actually work in the body, right? But anyway, so the shape of the orbitals is going to define the shape of the molecules, and that's what we're kind of interested in, right? So it's important to understand the shapes of an S versus a P, D, F, yada, 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 and see how that's going to affect the actual shape of the molecules that we're dealing with, okay? So we've got the 2, we've got the S. All right, so we talked about the different blocks, right? We have the S, the D, the P, and the F blocks right there. Our principal quantum number L, right? So our principal quantum number L tells us the shape of the orbitals that we're dealing with. Now, we don't care too much about the actual numbers for that, right? L is limited by how big N can be, right? So L is no more than N minus 1. Who cares? That's not really what we need to know right now. I'm just saying that if we are stopped on the street and somebody says, what's L? Well, that's going to define what the shape of our orbitals is, right? And then make sure you go in the opposite direction of that person because they're asking weird questions, all right? So that is, I think it's something called like the Azimuthal quantum number or something like that. Right? I forget exactly what the name of it is. It doesn't matter, okay? But we can solve for L, and that gives us the shape, right? So we have 4 answers for L, and those are where S, P, D, and F come from, okay? So not too important with that. M sub L. M sub L gives us the subshell. Now this is what's going to be important. This is something that is somewhat something a little bit tricky, I think, for some students. But there's no trick, right? Science doesn't have tricks. What does it have? Logic, okay? So M sub L is going to tell us how many orbitals there are in that shell. You guys with me? So taking a look at the P block here, counting left to right, starting at boron there. Boron all the way over to neon. How many elements are there? 6. Okay? So we're in our P block, and it takes 6 electrons to completely fill the P block. How many orbitals would that take? 3, got it? So what does that mean? How many p orbitals are there ever? 3. Am I saying this is a 3p orbital? No, I'm saying there are 3p orbitals. We would call them px, py, and tz. Okay? They are named after the Cartesian coordinates where they lie on the axis there, right? The xyz axes. Does everybody follow along with that logic there? If it takes 6 electrons to fill that block, only 2 electrons can live in an orbital. I need 3 orbitals to accommodate all 6 of those electrons. Everybody with me on that? Now let's think about this. Everybody's got a nice XYZ coordinate system in their head, right? Right, so just for simplicity's sake, what are the angles between X, Y, and Z? 90 degrees. So what would be the angles between the 3 p orbitals? 90. You guys with me on this? So the assumption is that those orbitals lie on those axes themselves. Okay? And so if the axes are 90 degrees, we assume all 3 of the p orbitals are 90 degrees from each other. The shape of those orbitals, I'm just going to erase this in the background here for simplicity's sake, or make it a little bit easier to see. The shape of a p orbital is basically like a little pinched balloon here, right? I'm going to do that in red. Okay. All right, so we have 2 little spheres that are kind of, it looks like they're pinched together in the middle. All right, so everybody's seen like those clowns or street performers that like make balloon art, right? You guys see, you guys know what I'm talking about? Like so they inflate a balloon and they kind of twist it and tie it and they make some different shapes with it. Pretty impressive what they can do, right? So if you think about it, if you imagine this is a balloon that you would kind of twist together, in our minds, because of the world that we live in, okay, we imagine that there's a piece of the balloon that's sitting right there in the middle, right, that connects the 2 parts together, okay? That's not the case with these orbitals. What's at the middle of those 2 lobes? Nothing.
The nucleus?
The nucleus. Can electrons exist at the nucleus? No, they cannot. What am I drawing a shape of? Probability. Okay? So what's the probability of something not existing? Well, that was a dumb way of asking the question. You guys get what I'm asking here, right? If something can't exist there, what's its probability? 0, right? So there is a node that's at the middle of this orbital. And that has 2 implications. 1, that means it's an area of 0 probability. That always sounds impressive. 2, okay, 2, there's a change in sign as we go between one node and the other. Now, this is not too important for us in here, okay? The reason why I'm telling you guys this is because when you look in your book at some of the pictures, you see it kind of fluctuates between red and blue colors for the little balloon images that they give you guys. That's not arbitrary. Okay? That's not because they had a big ink budget and they had to use it somewhere. There's a change in the sign of the function as it goes past the origin through one of the nodes. Okay, so we have a plus sign, we have a minus sign. Okay? We have a positive and we have a negative area. It doesn't matter which one's blue or red, which one's positive or negative. No. Is that going to be a big deal for us in here? Not really. But it's something important to keep in mind when you guys are dealing with all these orbitals and looking at those pictures. Okay? Yeah?
Sorry, so what I'm not understanding is, so S has 2 electrons, so it's only 1 orbital.
Correct.
So does
Per energy level.
Yeah.
Yeah.
So does that mean it's just X?
No, it's just an S, right? S is spherical. It exists on all axes, right?
Okay, but then what would you do for D that's 5 orbitals?
Do what?
For D, when it's 5 orbitals?
Yeah. So I'll tell you about those names in a second.
Oh,
Yeah.
okay.
Everybody with me on this about the whole plus, minus, red, blue, node, all that kind of stuff? Yeah.
If you're gonna get to this layer, that's
Sure.
fine, I'll wait, but, I've always wondered where, say it's carbon, like where's the S orbital gonna lie there?
Yeah, I'll see if I can pull up a picture for you, because it gets, I have a picture in my Gen Chem notes, so if you have my old Gen Chem notes, it's actually put in there.
Okay.
If you go take a look at this, it basically looks like a bunch of these balloons kind of all stacked on top of each other is what it is, right? So it looks really complex.
Okay.
Well, I'm not gonna argue about that, right?
Okay.
So, but it's kind of very, this is the problem, right? We're dealing with quantum chemistry, right, at a really small level. It's just a very different set of laws than what we deal with in day-to-day life, right? And so this is kind of the origin of quantum mechanics and how the world changed with, all the theories that got developed from that, right?
Okay.
It's a good question, right? I can't draw it, I'd have to go pull up a picture.
Yeah.
That's kind of what it is,
I
right?
think I'd like to see that.
Yeah, very interesting. Everybody with me on this though? Got that? All right. So L tells us that, M sub L tells us how many orbitals. M sub S is kind of the easy one here. This just tells us the spin of the electrons, whether it's spin up or spin down. Now up and down are obviously arbitrary, right? Because, you know, we just have to define something within our world, right? So they're just, electrons have to spin in opposite directions is what we're really getting to. If there's something that's spinning up, the next one has to spin down, okay? So by convention, we assume the first thing spins up and the next one spins down. Again, that's a little bit beyond what we need to talk about here, but maybe if you guys are going on to some advanced classes in chemistry, whatever that may be, then you guys will probably run into this again, is what it is, okay? For what it's worth, kind of as soon as you guys, if you were taking a chemistry degree, right? One of the other fields of classes which we don't teach here is called physical chemistry, which is you go through and break down the different formulas that actually come up with this kind of stuff here. And that's where a lot of these other kind of questions which you might have lingering there come from. How do we know these things? How can we prove it, right? Or the more important question is, who cares, right? So, what's up?
Did you say it's the spin of the electrons or
Yes.
the orbitals? Electrons?
Yeah, orbitals don't have a spin, they're just a probability, right? Yeah. Maybe I misspoke, but I mean the electrons, right? The spin of the electrons. Everybody with me on that? So we got these four numbers. The two important ones for us are going to be the N and the L, and then keeping in mind the M sub L, okay? Question. Our D block is in the middle there, right? If we count left to right from scandium all the way to zinc, right? We count 10, so how many D orbitals have to exist? 5, right? Now, we can't call them X, Y, and Z because that's only 3, so we have a couple different names for them. So if you guys remember on that worksheet that I gave you, they asked you to draw the X squared minus Y squared orbital. That is one of the names of those. That is the part of the function that describes the shape of the D orbitals, okay? Now, just for argument's sake, I'll draw it here. So here's an arbitrary coordinate system, okay? Here's our P orbital. Oops, didn't do that. I just wanted to do that. Okay. Here is our P orbital. Okay, that we just dealt with. Okay. A D orbital is going to look like 2 of these. Is all it is. Okay. So we would add another set of lobes here and another set of lobes here is what it is. All right. So it kind of has this cloverleaf shape to it. Okay. Guess what an F orbital would look like? That, but we add another set of lobes in a different dimension. Okay? Yeah.
But the orbitals still only hold 2 electrons.
That's
each.
correct.
So you have 2 electrons that are basically bouncing around freely in a cloverleaf path
Yep.
type thing.
Yep.
Why?
Each one of those.
Why?
Yeah, like what?
Why does the universe exist? Is that what you just asked me? I don't have a good answer for that. That'd be a philosophy question, right?
But no, I mean, okay, the s orbital, it makes sense to an extent, and it's kind of like micro.
You're asking how does one electron get from one lobe to the other?
Yeah,
Yeah.
and why would it swim in that like specific pattern type thing?
Because that's how that works. I don't have a better answer for you than that at the moment, to be honest. Right? I'm not trying to be coy with you. I don't have a better answer for why it has that shape aside from that's how the math falls out. Right? I can't philosophize about why that exists like that, right? I really don't have an answer. It's a good question, right? A really good question. I just don't have an answer for it. How does one electron get from one of the blues to the red lobes? That is because you are thinking of if I had a tennis ball and I threw it to you, it would pass through space to get to you. That's not how the quantum world works, right? That's the difference. So take a look at things called quantum tunneling if you want to take a look at that stuff. Right? Things just spontaneously exist in a different place, basically what it is.
Because God
And that is an answer that I would point to for sure, right? But this is a challenge. It's a good question, Rachel. The thing is, the problem is we're trying to apply our rational physics that we deal with in everyday life to these things. And it's a completely different set of rules. That's the problem, right? So I wish I was more eloquent in explaining this stuff to you. I'm not a quantum chemist though, right? That'd be a very good question for Dr. Sadasivan though, because that's his field of study, right? Relativistics and all that stuff is very much tied up with these kind of things here.
So you're saying I should screw with Dr. Sadasivan in physics today?
I would say you should ask him meaningful questions and you'll be impressed with the questions that you ask. That's what I would say. Cool. Okay, yeah, what's up?
But you drew it as a d orbital, right?
Yeah,
So there's still only 2 electrons in
Yep.
there.
any orbital, doesn't matter what the shape is, only up to 2 electrons, yeah. Yep,
I'm sorry, so all 4 of those, that's 2. It's not 2 and then another 2 in that one orbital?
any orbital, I don't care what the shape is, what the color, 2 electrons, that's it, yeah. I'm just saying that there's a different shape that looks like 2 P orbitals. I'm not saying those are 2 separate orbitals, that is one orbital,
Okay.
only 2 can live in there, right? Everybody with me on that?
So when you drew the P orbital there,
Yep,
there is one of those on each of the axes, or all 3 orbitals are contained in that one area of probability there?
are all 3 orbitals, I'm sorry, I missed something.
He's saying, are they overlapping or are they really existing at 90-degree angles?
Is that, did you draw like one third of it? Are they all?
This? Yeah, this is just the PX, right? The
Okay.
PY would be on the Y-axis,
Got
the
it.
PZ would be there, yeah. I'm not that good an artist, so I can't, that's the other end of this, yeah,
So they each exist on their own axis.
correct.
In the case of Z, since there's 4, like you can't have them not overlap.
In the case of Z,
Or not, sorry, Z, the D.
Yeah.
D orbital, like, so assuming that you have the maximum of 5 D
Yeah.
orbitals,
mhm,
are they just overlapping like crazy?
No.
Or,
they don't overlap.
what do you mean they don't overlap? There's so
I mean
many-
exactly what I'm saying, they don't overlap.
So the angles between them get smaller because they're.
So, you guys are going off the assumption that they all live on the axes themselves. They're off axes orbitals also.
Oh.
Yeah. Yep,
Sorry, so is each hourglass 2 electrons or
no, any orbital, 2 electrons.
so each like weird circle thing?
Nope, that is unorbital. I don't care how many I don't care how many lobes I put on there, that is just one orbital, 2 electrons live in there.
Anywhere within that area.
Anywhere within that area. Good?
No.
All
No.
We're
right,
gonna
we
need
do
it
have to, good questions, I do have to get to other stuff, right? So, I know it's stuff that's kind of a little bit mind-blowing here, but be happy to answer some other questions, swing by or chat with me. I can sit there and make you guys more confused, right? So, the point being this, all right? What I want you guys to remember is that these orbitals have a defined orientation. The PX, the PY, and the PZ orbitals are pointing in specific directions, and they have angles in between them that are defined by their geometric or probability, they're defined by their probabilistic shapes, okay? So a PX and a PY and a PZ are 90 degrees from each other. And because we're going to talk about how that impacts the actual geometry of the molecules that we make, that's where we're getting to with this, okay? Electrons do chemistry. If electrons live in orbitals, the orbitals, by extension, are the things that do chemistry, right? So we have to know where the electrons live, we have to know where the orbitals are, and then we can make a bond, and then we can finally do some chemistry, right? You guys following along with this? This is why I'm spending some time talking about these things. Because I'm going to tell you how these are lies. You ready for that?
Uh-huh.
Yep. No, they're not really lies, they're good lies though. Okay, so I think we kind of talked about all these different aspects here, right? So, so now that we know where orbitals live, we have to separate them out into 2 different categories, okay? So we talked a little bit about this last time, and I think you guys threw out some of the terminology and things as we were discussing this. But there are, in general, okay, if we're dealing on the atomic level, okay, just on the atomic level, not within a molecule. On the atomic level, there's 2 types of electrons. Do you guys remember what those names are? It is a great question. I'm really good at this. I'm great at asking questions. Yeah, what's up?
Valence,
There's valence, and what's the other one?
core,
Core, okay? So there's valence electrons, there's core electrons, okay? What does chemistry?
The valence electrons.
The answer is both of them, right? What's the better answer that you guys wanted? 99.99% of the time for the stuff that we're talking. In fact, you know what? I'll go ahead and say 100% of the time for what we're talking about for any chemistry class that you guys take here, it'll be valence electrons. We're not really doing anything with our core electrons, okay? That has to deal with some kind of, I guess a little bit more in the nuclear realm of things we could say about that, right? But for our purposes, it's going to be valence electrons that do chemistry, yes?
So if we find something in this class or another class where we are dealing with core electrons, do you have to like eat your hat or something?
Sure, yep. I know we're not doing it, so I'm very confident about that.
You did design the course.
Yeah, I've been to, it's only my third day, so maybe I made a mistake, right? Anyway, so we need to know what a valence electron is, right? Aside just being able to give it a name. All right, so where's the core of the Earth?
The center?
In the middle of it, right? Where's the core of an apple? In the middle of it, right?
Well,
So we have we have the core, and we have all these different parts, and all the way on the outside of the Earth is where we live, right? So we would be the valence electrons for the Earth. The things are on the outermost perimeter, the outermost shell, okay? The skin of the apple we might consider the valence shell for an apple itself. The things are on the outside. You guys get what I'm saying with this? The valence electrons are on the outermost part of the atom itself. Yeah,
if the Earth is an atom, is the moon an electron?
could be, right? I mean, you're the one who's making up this universe where the Earth is, you know, just,
You were using the Earth as an analogy.
yeah, I didn't say it was real, but anyway, so, you guys get what I'm saying with this? Okay, so take a look at a periodic table. How many valence electrons are there in sulfur?
6,
How'd you guys get that?
column.
Okay, so there's a couple different ways, right? Let me make some space here. Just clean things up a little bit.
Oh, wow, that's beautiful. Lots.
Alright, so if we are looking at our buddy sulfur over here, okay, to get the valence electrons for that, technically what you guys are doing is starting at hydrogen and getting the complete electron configuration and get all the way over to sulfur, right? So you do 1s2, 2s2, 2p6, right? You guys following along with this? You guys remember this stuff, right? Then we hop down here, 3s2, 3p1, 2, 3, 4, right? 3p4. Everybody good on that? Does that sound familiar? Remember that now, right? So technically that's what we should do, right? There's a definition for valence electrons, right? It's any unfilled or partially filled orbitals, okay? Let me clarify that. Excuse me, I misspoke there a little bit. It's any partially filled orbitals, okay? And your s electrons are always going to be valence, okay? So always your s electrons in any partially filled orbital. You're about to use up your allotment for questions for the day. But go ahead. What's up, Rachel?
In the case of the one below it, selenium, is it would it be 16 because you're counting the D's, or would it still only be 6?
Good question. Who wants to answer that? So the question is, how many valence electrons does selenium have? What's the definition of a valence electron? Your s orbitals in any partially filled orbitals. To get to selenium, where do I have to walk through? I have to walk through my entire D block. Is that partially filled?
No.
No. Is it completely filled?
Yes.
Is it are those valence electrons?
No.
No. Got it? What's up?
You said it's any partially filled orbitals
Yep.
and s orbitals. So
Yep.
would not 1s2, 2s2, and 3s2 also be valence shells, or is it the
Okay.
closest?
So remember the picture I tried to paint for you, right? So remember the core is in the middle and we're on the outermost. So we're always dealing with the outermost s, right, in any partially filled orbitals. Okay? Good question. Everybody follow along with that? I'm not saying every s orbital is a valence. I'm saying the outermost, the skin of the apple, the crust of the earth, that kind of thing. Good? All right. So if these are valence electrons here, let me just do that in red. Right? If these are valence electrons, then all the rest of it has to be core electrons. All right? So if you're not valence, you're core. Good? Cool. How important is it to know your valence electrons? Very. How often are you guys going to do this in this class? Every day. Okay? Every time you guys draw a Lewis structure, you guys are going to be counting valence electrons. Okay? Now, at the beginning, it might be that you guys have to physically sit down and count them and do all that kind of stuff. And that's fine. Okay? But through practice, you guys are going to be doing this subconsciously. Okay? You have to. Now the problem is when something becomes a reflex or when it becomes so trained, right? For those of you guys who are in athletics or any of this kind of stuff, you probably have talked about this before, right? The whole idea of muscle memory, right? What happens with that? You just kind of, your body's just so used to it, doesn't even have to think about it anymore, right? It's the same thing's going to happen when you guys are drawing Lewis structures. And what happens in this class when you stop thinking about what you're doing?
You make mistakes.
You make mistakes, okay? So this is where one of the mistakes happen. You guys stop asking the question of how many valence electrons does this have, okay? What does chemistry? Electrons. Okay, how does organic chemistry work? Something negative. Now we can fill in the blank. Some electrons, right, seek after something positive, right? Something negative, electrons seek after something positive. If I forget where my valence electrons are, the things that do chemistry, guess what I just missed? The first step of organic chemistry. Got it? So it's going to be important to keep this stuff in mind and not forget how many electrons you have and lose count of those kind of things. Okay? So I saw a couple of questions. I don't know. Yeah, what's up?
So I remember that there is, we haven't worked with the transition metals a lot.
Yeah.
That being said, it's important in finding valence electrons and where they're coming from.
Mm-hmm.
I remember there's a case where if it was like, there's like 9 or so, it's
Yeah.
still some of the S.
Yeah.
Some of the S orbital.
Yeah. So this is something that we talked about in general chemistry, where there are exceptions to this kind of rule. And so things like copper and chromium are going to have a little bit of a weird electron count because there is something that happens with a half-filled orbital set. Right now, we're not going to deal with that too much in this class. This is kind of something that we would talk about in general chemistry and inorganic chemistry. If you guys ever, if I ever get a chance to teach my bio and organic class here again, I would talk to you guys about this because it is something important. Remember, the reason why I chose to become a chemist is because I'm not smart, okay? And I mean that in a lot of ways that I'd probably hurt myself. Ouch. Right? But what I mean is I can never be wrong because there's always going to be an exception to something. And so when you guys say, Dr. H, you said something wrong, be like, no, I found this exception, right? Okay. You guys get what I mean with this? So here's one of the frustrations that happens with students sometimes, okay? Especially for a class like this. Remember, I cannot give you all the answers. And what does that mean for you guys? I don't expect you to have all the answers, right? What do I expect you to be able to do? Rationalize towards the answer that you guys did give. I think this is the major product of this reaction because I see blah, 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 right? You guys can rattle off some evidence for that. You guys get what I mean with this? But there's always going to be side reactions that happen or exceptions or other things along the way. Does that make sense? Yeah, what's up?
This might sound like a dumb question, but if you have a situation where you're looking at, let's say, nitrogen, for example, where it has partially filled p orbitals and still fully filled s orbitals, which orbital is the one that's going to be considered valence?
Both.
But they're
Both are considered, well, they're not, the orbital, they are both valence electrons, right? Or excuse me, both those orbitals have valence electrons in them. I think that might answer your question, right?
I guess my question is which orbital is most of the chemistry going to be coming from?
So hang on to that thought. Hang on to that thought. Anything else? Cool. All right. Is everybody with me on that? All right. Valence electrons. Got it. Okay. So now that we have valence electrons and all those kind of things, okay, now we can ask the question of what in the world can we do with valence electrons? Well, once we identify valence electrons, there's only 2 things we can really do with them, okay? Valence electrons only can ever do 2 things. They can make a bond, or they can exist as a lone pair, okay? Now, lone pairs can go on to make bonds, and bonds can go on to get converted back into lone pairs. You guys catch what I mean with this? So there's really only 2 things where we're ever going to see valence electrons, as lone pairs or in bonding pairs, okay? I think in the book, that's where they kind of talk to you guys about whether things are monovalent or divalent or these kind of terms that they use there, right? I don't like that because then you guys kind of focus in on, oh, this is only ever going to have 2 bonds to it or these kind of things. That's not the way you guys should approach that, okay? I'll tell you what I mean here in just a minute. Question? Our good old buddy, carbon dioxide there. Okay? Can you guys draw the Lewis structure of that? All right, go for it. Be careful, what did I say about muscle memory? All right? Some of you guys might be very well practiced in drawing Lewis structures, but start to think about the steps that you're taking, okay? And why you're taking them, and can you explain that? Well, how do I draw a Lewis structure? Yep,
Start by identifying how many valence electrons are in each atom.
good. I need to know how many valence electrons there are first, okay? I've got carbon, how many valence electrons does it have? 4. I've got 2 oxygens, each one has 6, or I got 6 plus 6 plus 4, right? So 16 total. Count your total number of valence electrons, that's step number 1. Right, so 16 total, good? Step number 2. All right, step number 2 is what we'll say is put together the skeletal structure. That means we put all our atoms there and connect them with single bonds. This is important, and this is where some of you guys missed stuff on that worksheet already. Did I tell you guys my secret? So really I'm in my 60s, okay? All right, now you guys don't believe me. You're like, wow, what's his secret? I'm kind of like a vampire, okay? I live and feed off of missed points from students, right? So you notice how young I look is because you guys miss a lot of questions. I'm just kidding. I don't ever want to. I'm not really in my 60s, okay. But the other stuff, yeah, okay. The point being this, right? I am never going to try and trick you guys. You know why? I am giving you the steps to make sure you get everything right. Where's the problem going to happen? When you guys say, what does he know? I'm going to do it my own way, okay? And that's where you start to miss steps. Now, just get into the practice, and if you develop the practice well enough, then you can start to skip some steps. Here's my my bargain that I make with every one of my students, okay? Ever. I don't want you guys to skip steps, but I do skip steps. Sometimes, not when I'm teaching you guys, okay? So what's the difference? I will allow you guys to skip steps when you get your PhD. Sound good? So you guys have between now and Monday, right, to find an online program. Get your online doctorate, and then you can come and skip steps. Sound
You
good?
never said it had to be in chemistry.
I didn't say that. You're right. You can do whatever you want to, right? A doctorate of, I don't know, figure something out. Mushroom, mycology. There you go, okay? So, all right. I was watching a cool movie last night on Netflix about mushrooms. Absolutely fascinating photography.
mushrooms.
Huh? No, yeah. Unfortunately, it devolved into kind of the whole magic mushroom kind of thing at the end. But so it wasn't that great a movie, but the cinematography was absolutely amazing because they had a bunch of these time-lapse shots of like mushrooms growing and things.
Like Planet Earth stuff?
Yeah, exactly. They're just amazing, just absolutely amazing stuff. So watch it on mute, and then skip this later. Alright, so we need to draw a skeleton, okay? So what do I mean by a skeleton? We need to have something in the middle and everything else is connected to it, right? So kind of like you have your spine and everything else kind of works off of that sort of. I'm not a, well, of course, you know, my expertise is anatomy, as you guys can tell, right? You guys get what I mean? We have to have something in the middle and everything else comes off of that. How do we pick what goes into the middle?
The least electronegative?
The least electronegative?
The one with the most, bondable valence electrons.
The one with the most bondable electrons?
Or least.
Or least, so anything in the universe, okay.
Usually carbon.
Usually carbon. Yeah,
Just the one that can make the most bonds.
the one that can make the most bonds. One of those is correct.
The least electronegative.
It's the least electronegative, okay? Now, can the least electronegative make the most bonds? Sometimes, sure, okay? But in general, we will start with the least electronegative, okay? Sometimes the book says the biggest atom, that's not true, right? I'm not saying this book, terrible books, okay? They give you some different rules and things, okay? There are going to be some exceptions to this, okay? Now we're going to see when those exceptions come up. But in general, remember, I'm giving you the rules for, let's say, 90% of the time, this is how it works. Got it? Okay? So least electronegative. Carbon, then we'll put an oxygen on both sides and we connect everything with single bonds. Good? That's what I mean by skeletal structure. We pause, we take a minute here and ask, what is electronegativity? Now we talked about this, right? It's the ability of an atom in a molecule to attract electrons to itself. And I asked you the question, how in the world can we make an atom attractive for electrons? And this is where we launched a discussion of orbitals. Okay? We talked about energy states and all that kind of stuff. You guys remember this? Yes, a little bit? Okay, remember, the more electronegative atoms, okay, are going to be smaller in size. Does that make sense? Okay, why does that make sense? So two people nod their heads. Ayuni, why does it make sense? Why are more electronegative atoms smaller in size generally? Yeah.
I was gonna say because they have the opposite trend as radii.
That's true, right? Yep.
Because they can get closer together. Like
What can get closer together?
the nuclei.
So remember, we're dealing with an individual atom here. What makes an atom more attractive to electrons? Yeah.
Well, I was gonna say they're like smaller because they're more attracted to the protons and
What's more attractive?
the electrons.
You guys got that? What's the only thing in the world that's attractive to an electron? Is it a nice pool in the backyard? Right? A good 401k program? Right? Is that what it is? No, that's attractive to a chemistry professor, okay? Right? What's the only thing that attracts an electron? A proton. So what would make something more attractive? Well, the closer it can get to the nucleus, where protons exist. Everybody with me on that? So why are smaller atoms typically more electronegative? Because what are we measuring with the radius? We're measuring the distance from what? The nucleus to the outermost shell. Got it? If that outermost shell where electrons go into or out of is closer to the nucleus, the more attractive that is for electrons. Got it? Everybody with me on that one? Okay. Now remember, we put the least electronegative in the middle typically. Here's carbon. Carbon is less electronegative than oxygen. What's oxygen's ranking in terms of electronegativity? For all of the elements on the periodic table, oxygen is number 2. Okay? The second most electronegative atom on the periodic table. What's number 1? Fluorine. Fluorine number 1, oxygen number 2, nitrogen number 3, and chlorine number 4. You should keep that in mind. That is one of those very, very important things to think about. Okay?
What's number 3?
Nitrogen.
Nitrogen is 4.
Nitrogen's number 3, chlorine's number 4.
Oh, okay.
Yeah. Different books are going to argue with me, but I will fight back. I can prove it. Good? Know your top 4 electronegativities, okay? All right. So oxygen's more electronegative than carbon, so we put that on the outside. Everything's connected with single bonds. Let me change colors here real quick. Okay. What am I representing with those green lines?
Pairs of electrons.
I'm representing sigma bonds. Okay. What else am I representing? Shared electrons. Okay. What else?
Pair of electrons.
A pair of electrons. So let's stop here for just a second. If I am saying that that green line there is representing a pair of electrons, what does that mean? I have 2 electrons, which means electrons have to live in orbital. So which orbital is there? Is it an S? No. Is it a P? No. Is it a D? No. Is it an F? No. What is it?
Is it a molecular orbital?
It is a molecular orbital. Are we dealing with atoms? No, we're now dealing with molecules. Okay? Now, here's a question. How do I build a molecular orbital? Molecular orbitals are built from what? Atomic orbitals. Got it? So we're going to talk about this in just a second. Okay? Yep.
Would that be the same as a hybrid orbital?
Yes. Yep.
It's also a sigma bond, right? Because the sigma bond is made out of the first molecular orbital.
Okay, so we got 2 flavors of bonds that we're going to deal with in this class. We got sigma and we have pi bonds. Those are it. Okay, there's other bonds that exist, but for the most part, we're going to deal with that. We will talk about something called 3 center 2 electron bonds later on as we get towards the other chapters in this class, but it's not going to be that important for us. Okay. So sigma and pi. All right. Now, in general, we can say that any sigma bond is a single bond for us, okay? Right, so a sigma bond, right, just represented by the crappy sigma symbol that I can't really draw all that well. Right, the little O-looking thing with the hat coming off of it, right? Where are those electrons living? Well, they're living in a sigma orbital, okay. Where is that orbital located? In space. Relative in the molecule there. Yeah.
I don't know if this is the right word, but I'd say that planar to the molecule, the same plane.
The same plane of what? What are you defining as your plane?
Well, it's a linear molecule, so
Okay.
We could say, I mean, it's floating around, so we could just call it the X plane, the X.
So you're saying it lives in between, exactly in between, in the middle, between the carbon and the oxygen. That is exactly correct. A sigma bond has its electron density between the atoms themselves. Okay? That's going to be important, so hang on to that thought. So electron density between the atoms. Why am I spending time talking to you guys about this? Hang on just a second. Why am I spending time talking about this? What does chemistry? Blah, 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 right? Negative does positive, blah, 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 right? If I have electrons that are in a sigma bond, they're going to behave differently than other kinds of bonds. You guys with me on this? Because they're living in a different place, at a different energy level, right? All this kind of stuff that goes along with it. So it's important to think about these things, right? You guys just drew a simple line on your paper, right? And now we just spent the last 10 minutes talking about that simple line. Is that just because I need to fill time? Yeah, I didn't prepare any notes, right? Oh my gosh, I gotta just improvise, okay, right? No, it's because that's gonna be extremely important, okay? Yeah, what's up?
The sigma bond isn't in the middle exactly though, right? It's just between them and then it's blue.
Yeah, so this is a fair point, right? So if you look in reality, okay, I'm lying to you guys, but you guys already knew that. Why? Because I lie to you guys all the time, okay? So in reality, what I'm talking about with bonds are not just existing between discrete atoms themselves. This is something that's kind of a little bit different. The book does a good job explaining this, okay? So if I wanted to be technically correct, what I would say is that we are representing a molecular orbital that encompasses all three of the atoms, and the majority of the electron density lies in between the atoms themselves in the plane of the atoms. Okay? You guys catch that?
No.
Majority of the electron density lies in the plane of the atoms between the atoms. Okay? Does that mean there's some that extends beyond it? Yes, it does. Okay? And that's going to be important, and we'll talk about why that is too. Molecular orbitals actually encompass an entire molecule. It's not in between discrete atoms. Okay? This is something that's a little bit different for us to think about. You guys think that this one bond represents just electrons being between these here. That's not true. They're actually shared between all three of those. Okay? And we'll come back a little bit to this idea of the more complex level of molecular orbital theory when we get to the second semester and we talk about the Diels-Alder reaction. Okay? It's going to be important there. That is a fair point. Okay? Now, why am I telling you guys this pile of lies then? Because this is how we're going to be able to treat it and simplify molecular orbital theory. Okay? My job is to teach you guys how to be successful at chemistry 90% of the time. Right? 90% is an A, is that okay? Maybe 92, have a little flex room in there. Okay? For our purposes and how we're going to treat it, a sigma bond is in between two discrete atoms themselves. Okay? And we assume that that lies in between the plane of those. Okay? Is that 100% correct? No. Will that help us facilitate how we can do our reactions and explain the reactions? Yes. Okay? Everybody with me on that one? All right. Cool. So we have that right there. Okay, so we're still not done here. What we do once we've drawn our skeleton is we count how many electrons we've used. To make a bond, I need 2 electrons. To make any kind of bond for us, I need 2 electrons. This is important, okay? 99% of the time, we're going to be dealing with lone pairs turning into bonding pairs, and bonding pairs turning into lone pairs. You guys with me on that? That's really the only cycle that we're in. Lone pair, bonding pair, bonding pair, lone pair. Make a bond, break a bond, make a bond, break a bond, okay? This kind of thing. So if I started out with 16 electrons, okay, and I used up 4 of them there, that means I have 12 electrons left over that I need to do to fill in, right? Fill in my octets. Okay. Now, this is always one of those things that everybody kind of, or usually sticks pretty well from Gen Chem. We talk about the Octet Rule, right? Everybody kind of remember that? Sounds familiar, these kind of things? What did I tell you guys about the Octet Rule, though, when you guys heard me talk about it? It's crap, okay? It only applies to 4 atoms out of the 92. What a useless rule, right? It applies to carbon, though. It applies to nitrogen. It applies to oxygen, and it applies to fluorine. Okay, so carbon, nitrogen, oxygen, and fluorine. Those 4 exclusively follow the Octet Rule. Except for carbon when it decides not to. Got it?
What?
99% of the time, okay, carbon, nitrogen, oxygen, and fluorine are going to be following the Octet Rule. Why is that useful information to keep in the back of your mind? What is organic chemistry? Science of carbon. Got it? So if carbon is going to be following these octet rules, that's probably pretty good to kind of at least keep that in mind. Okay? And when it's not following the rules, we need to pay attention and say, hey, something odd is going on here. I better pay attention to it. Everybody with me on this? Okay. Now what is the octet rule? The octet rule basically says that every atom wants to get to a full valence shell. Good? Okay, so if we take a look at our buddy carbon or the sulfur that we were working on earlier, right? Take a look at your periodic tables. Okay, what are the orbitals that are involved with the valence of sulfur? We had our what? Our 3s and our 3p. How many p orbitals are there? The px, the py, and the pz, right? So our s and our 3p orbitals for a total of 4 orbitals. How many electrons can, who said 3? All right, I'll let you bring a calculator to the exam. That's good. Right? So a total of 4 orbitals. How many electrons can live in each orbital? 2. So 4 times 2 is 8. Got it? So the whole idea is, okay, we want to give access to 8 electrons for every atom. Now, as flippant as I am about the octet rule and saying that it really doesn't apply to much, it is a good place to start. That is why we teach this to you guys, okay? In general, we want to satisfy the octet rule, even if the atom itself doesn't necessarily adhere to it strictly. It's a good place to start, okay? You guys following along with this on that one, right? We start there and then we kind of adjust as we need to as we go through. But we understand that carbon, nitrogen, oxygen, and fluorine, they're always going to be following these things. Good? All right, so question. Right now, the way I have it drawn, how many electrons does oxygen have access to? 2, got it? Right, carbon have access to 4 and oxygen have access to 2. Everybody with me on that? So when we're talking about access to carbon, access to electrons, we're just counting lone pairs and bonding pairs. That's what we mean. And somebody, I forget earlier, maybe Maria said, right? We're talking about sharing electrons. We'll talk about covalent and polar covalent, that kind of stuff in just a minute. Okay? But when we're talking about satisfying the octet rule, we're counting our bonding pairs and lone pairs together to get to that 8. Everybody with me on that one? Okay, so fill in octets. When I fill in the octets, where do I start? I am filling in electrons. Logically, that means I should start filling in electrons on which atoms? The most electronegative, the ones that are usually on the outside, the periphery, okay? So oxygen right here only has access to 2, so I'm going to give it 4, 6, 8. Got it? Alrighty, so I filled in my 12 electrons there in blue, and we're done. Okay, I just drew a Lewis structure, right? Yeah, don't shake your heads, I'm not wrong. How dare you try to... Did I follow the rules that we have so far? Yeah, I did. But the 4th rule is the most important rule. Okay, and this is the one that you guys are going to skip over. Okay?
Formal charges?
More specific than that.
Check formal charges?
We have to check our answers, check our structures. We used 16 total electrons. You can go through and count all up there, right? We drew a skeletal structure. They're all connected by a bond, all these kind of things. Well, we need to make sure this is the correct answer. Okay, so first thing we need to check. Yeah. Can't spell this morning. Correct number of electrons. Did we add or remove any electrons? Did we forget some electrons or anything? Well, fortunately in this case we didn't, right? So always double check yourself, make sure you didn't just add a lone pair in there. Very common thing that happens sometimes, okay? Is anything missing in octet?
Yes.
Yes, we are, right? So the 2 oxygens have access to an octet. The carbon in the middle doesn't, okay? I'm going to introduce to you what is going to be the bane of your existence for the rest of organic chemistry, and even biochemistry, okay? So if I want to give that carbon access to more electrons, what do I need to do? I can't just manifest electrons and draw lone pairs on there, right? That would be violating the correct answer, step 1 there, right? So how can I give it access to more electrons? Now you guys know the answer, it's what?
Make another bond.
Double bonds. Where do those double bonds come from?
Oxygen.
From the lone pairs on the oxygen, got it? So watch this first, okay? Follow along. What I'm going to do is I'm going to show you guys how we move electrons in organic chemistry. What we're going to do is look at arrow pushing, okay? This is your fundamental key tool that you guys are going to use to tell me how reactions happen. One of the questions that's going to show up on the exams is, how does this mechanism work? And you guys are going to have to use arrow pushing to show that for me. Okay, what did I say is the most important rule in chemistry, the organic chemistry? Something negative goes to something positive. And somebody asked the question, Why am I very specific about it being from something negative to positive? Because what does chemistry? Electrons. So when I push arrows, when I'm showing the movement of electrons, I always start from where the electrons begin to where they end up. Everybody with me on this? Where they begin to where they end up. I am moving electrons. I'm not moving an atom. Okay? I'm moving an electron. Now watch, everyone up here real quick, okay? I'm going to do some things and I'm going to come back and kind of correct you. So give me a minute. Let me, work through my thoughts with you guys, okay? So take a look. Essentially, I'm going to be wanting to make that orange bond right there. Everybody with me on that? So I have to, my electrons are going to start out at this lone pair here and end up between the carbon and the oxygen as that double bond there. Everybody with me on that? So here's how I'm going to represent that. I represent that by drawing a double-headed arrow, okay? The origin of the arrow starts at the electrons and it points towards where they end up. Everybody with me on that? Okay? This is what arrow pushing mechanisms are. This is what arrow pushing is. Where the electrons start to where they end up. Good? Yeah?
Does it matter if you lose the top pair and the bottom pair?
Does it matter? No.
Like, double-headed as in it's the normal arrow. Like,
But it's specific because later on we're going to introduce single-headed arrows. That means something else.
Yeah, no, I thought you were saying that both sides had like
Yeah. So yeah, this is what I mean by double-headed arrow like that,
Okay,
right?
okay. So
A
it's not
single-headed
like a
arrow
triangle.
will mean something else. It would look something like
Something like that.
right?
Okay.
So, but yeah, it does. There is a difference in between. In fact, we talked a little bit about this in Gen Chem. Arrows mean a lot of different things, right? Equilibrium arrows, reaction arrows, mechanism arrows, all this kind of stuff. All right. So what we're going to do is take a lone pair from each of the oxygens, right, and give that to as a double bond, right? I'm going to do something different though. Okay? I'm going to disagree with you guys. What I'm going to do is this instead. Sound good? Let me draw what I'm doing. There's my carbon. There's my oxygen. There's my oxygen. I have a bond in green over here. I have a bond in green over here. Okay, this side over here is left alone. I made a bond in orange. I made a bond in black. And I have this lone pair over here. Hang on a second. Everybody, first and foremost, before you guys rush off to tell me how wrong I am, okay? Does everybody see how these arrows represent the movement of electrons and where we made these bonds here come from? This is going to be one of these key things I'm going to ask you guys to start to practice and think about. We're going to start to be looking at using these arrows every day with that, okay? So that's one of these key things. Good? All right, so here's a little bit of homework or whatever it is. Prove me wrong. This is a correct Lewis structure for CO2. I would venture that none of you guys drew it though, did you? Uh-oh, am I wrong? I'm saying this is valid. But remember what I said about chemistry. What are we trying to go for? Can we justify why that is or isn't right versus what you guys drew and whether that is or isn't correct? Sound fair? All right, so I'll see you guys on Monday, and we'll continue on with this. Yeah.
So,
Maybe not necessarily different problems. We'll talk about why also.
does it take your doctor